Hi there, welcome to your lesson on binomial distribution, expected value, and variance. Let's remind ourselves of some key statistics. There are what are called the measures of spread, and these are variance and standard deviation. They tell us how spread out a data set is. And there are measures of central tendency, such as mean, median, and mode, and these tell us about where the center of a data set is. Here's an example of two distributions. This one here in dark color has a low variance. You can see that if the mean is the middle value, the data set is spread out not too much from the mean in the middle. Whereas this lighter shaded color here, if the mean is in the middle here, the data you can see is spread out further. So higher variance, lower variance. That's what variance tells us. And variance can also be calculated further to something called standard deviation. So this is low standard deviation and this is high standard deviation. Okay, so here's three other examples. Looking at these three, tell me which one has the lowest mean. And now tell me which of these has the highest variation. Great, I hope you understand the idea. Let's continue and look at another example of that. So here we have a distribution of data as well. This shows, I guess it shows you average weather or climate in a place. You can see here, this curve, we have more colder weather and less hotter weather. But then if the whole curve shifts to the right, notice the curve has the same shape, but it's shifted to the right. That means the mean has increased because the mean is the average, which would be the middle value, which is like where the top of the curve is. The mean has shifted, so the average temperature has gone up, but the variance remains the same. That means the difference between low and high ones remains the same. Now compare that to this. We have the same climate situation where we have the original one here in the middle. You can see the mean in this case for both curves is the same. The average temperature is the same, but the second longer or wider curve shows more variance in temperatures. So more cold temperatures, more hot temperatures. Okay, so that's variance and mean when we look at distributions or curves. So now, let's get into the two main topics of this video, which are expectation and variance. So that's why we did the introduction, so we can understand what expectation and variance are. So for a binomial distribution, the mean value is called the expected value. Okay, so the average value is called the expected value. To find this, we will use this formula here. Expected value of random variable x equals n times p. That means number of trials times the probability of the success of that trial. So let's look at this example here. You flip a fair coin 8 times. What is the expected number of heads? Well, first of all, our binomial distribution looks like this. So random variable x is distributed binomially with 8 trials, and a probability of success or getting ahead is 0.5. We're assuming the coin is fair. So now let's use the expected value formula. So the expected value, or the mean value of this coin flipping situation, is 8 times 0.5. That's all we do. And what's 8 times 0.5? 4. Now let's talk about that in context. If you flip a coin 8 times, and there's a 50-50 chance of getting a head or a tail, then you can say I expect to get 4 heads, because 50% of the time I expect to get a head. So that makes sense. That's what expected value means when we talk about binomial distribution. It means what is that number of times you're expected to get that, and it's 4 in this case. Let's look at situation number B here. What was the expected number of raw eggs in our egg roulette experiment? Remember, when we did the egg roulette experiment, we used these conditions here. We ran 3 trials, and the probability of getting a raw egg was 2 out of 5. Okay, so what's the expected number of raw eggs somebody would get if they were crushing them on their forehead? All right, using expected value formula, we do 3 times 2 over 5, which is 0.4, and it is 1.2. So if you grab 3 eggs randomly from that bin we had, where 2 of every 5 eggs are raw, it would be expected that 1.2 of the eggs you grabbed would be raw eggs. So expected values can be decimal values. I know it doesn't make sense in the context, but they can be. Averages can have decimal values, right? Okay, C. A biased dice is thrown 30 times, and the number of sixes seen is 8. The dice is then thrown a further 12 times. Find the expected number of sixes in these 12 throws. So why did they give us information about 2 experiments. The reason is that for the first information it gave us 30 throws and how many 6s occurred, that's giving us a baseline, or basically we can use those values to calculate the probability, right? Because we ran, this is kind of a large experiment, we can say it's large, 30 rolls, and we got 8 6s. So we're going to use that to establish our probability. Okay, so that means our probability is 8 out of 30 will tell us 8 out of 30 times we'll get a 6. That's our probability, because this is a biased dice. This is not a normal die, which is fair, where the chance of getting a 6 would be 1 in 6. Here we can see it's an unfair die, and there's a chance of 8 out of 30 to get a 6. Okay, so we use that probability that we established in that first experiment to find the expected value in our second experiment. So here's our binomial distribution. We run 12 trials in this second experiment, and we know from the first experiment our probability is 8 out of 30 to get a 6. So what's the expected number of 6s in this second experiment? Well, we run the expected value formula, and we get 12 times that probability, which works out to 3.2. So if we throw the die 12 times, we expect to see 6 3.2 times. All right, great. Pretty basic formula, but an important idea underneath it, so I hope you're grasping this. Let's jump now to variance and deviation. So variance is a measure of the dispersion, which means the spread of data. For a binomial distribution, this value is found using this formula. So the variance of random variable x is equal to n times p times q. N again is number of trials, p is probability of success, and q is probability of failure. Okay, so standard deviation now, you may remember, when we have variance, to find standard deviation, which can be shown using this symbol here, sigma, it is the square root of the variance value. So here's variance, square root of that is standard deviation. Let's apply it here. So again, back to the coin situation. You flip a fair coin 8 times. What are the variance and standard deviation? So again, here's our binomial distribution. Variance, we're going to use this formula. So variance is 8, number of trials, times probability of success, times probability of failure. That gives us a variance of 2. Standard deviation is just the square root of that, so standard deviation is root of 2. Next one, what are the variance and standard deviation for our egg roulette situation? Oh, sorry, there's the value of that, 1.41. Okay, so that distribution again was 3 trials, probability of success, 2 over 5. So variance will be 3 trials times probability of success times probability of failure. That means not getting a raw egg. And notice this value, of course, can be obtained by taking 1 minus this one, right? It's a complement. And now our standard deviation, that works out to 0.72, and our standard deviation is this, which works out to 0.85. Okay, see if you can figure out the last one. C. In a large company, 80% of workers travel to work using public transport. A random sample of 15 workers is selected. Find the expected number of workers that take public transport, the variance, and the standard deviation. Try that now. Okay, here's our binomial distribution, 15 trials, 80% chance they take public transport. Here's our expected value, which is 12. Here's our variance, which is 2.4. And here's our standard deviation, which is 1.55. Okay, let's finish off with a couple more. Here's another one. Please read this and see if you can find A, the probability that a 6 will occur twice. Okay, this one is just like the one we just saw. There's an initial experiment which is used to establish our theoretical probability, and then there's a second experiment for which we want to calculate the values. So we're going to let x be defined as the number of 6s in 12 throws. The probability from the first experiment is 12 out of 50, 0.24, and therefore our binomial distribution is this. So the probability is 6 will occur exactly twice. Well, that can be calculated by running a binomial distribution, right? We have 12 trials, we want success twice. That's our combination that tells us how many paths, and each path has these probabilities, 2 successes and 10 failures. Run that like this. You could have alternatively run a binomial PDF to get that value, right? But it's really important that we keep going back to the binomial formula here so you really understand how it works. Okay, next, expected number of 6s is this, and the variance of 6s is this. Great problem. It connected our last few topics all in one here. Let's go on to one more. So from our practice assignment, to get you started on it, I chose this problem. Kind of a tricky one. Let's see if you can figure it out. So read the situation here, and then try A. Okay, A is tricky. Let me help you through it. First of all, we need to get the probability of having a girl be born, right? So we know to find a probability, we always take the number of occurrences of that thing divided by the number of total possibilities. In this case, how many girls in total are there? From this table, this represents 100 families and it says how many girls they have, right? So 13 families have 0 girls, 34 families have 1 girl, 40 families have 2, and so on. Okay, so how many girls is there? Well, if 13 families have 0 girls, there's 0 girls there. 34 families have 1, so that's 34 girls there. 40 families have 2 girls, so that's 80 more girls there. And 13 families have 3 girls, which is 39 more girls. And in total, if there's 100 families, and these are all 3 children families, there's 300 total children. So that's how we find our probability, because we always need our probability first in order to run the expected value or anything else, right? So that's the probability. Here's the number of girls we have, and here's the total number of children. And what that gives us is this, 153 over 300, which works out to 0.51. And that number makes sense. We know in general in human populations, male to female births are about 50-50 in general, right? But actually female births are a little higher around the world. We see that in statistics from around the world. So there's 0.51. Okay, so now that we've established our probability using the table we were given, we can answer question B. So another sample of 100 families is taken now, each with 3 children again, and we are calculating the number of families in this sample that you would expect to have 2 girls. All right. Okay, so what we found is the probability of there being 1 girl born when there's a birth, right? So a family has a baby, there's a 51% chance it will be a girl. So now we need to figure out, well, what's the chance that a family of 3 will have 2 girls? So that's a binomial distribution. Imagine a tree diagram that shows for one family, 3 births, and you follow a path. Girl, girl, and then boy, or girl, boy, girl. Anyway, there's several paths that lead to 2 girls. And we can find that using binomial distribution, right? So here's our binomial distribution. How many girls is binomially distributed? 3 trials, 3 children for one family, and this chance of getting a girl. And we're looking for probability that the family has 2 girls out of the 3 trials or the 3 births. So calculate that now in your calculator using binomial PDF. Okay, we get this chance. So there's a 38.2 chance 38.2% chance that a family will have 2 girls when they have 3 births. All right, but that still doesn't answer this question. So what's the expected number of families in this sample that you would expect to have 2 girls then? So we have a sample of 100. We're going to use our expected value formula now. And expected value tells us the sample size times the probability, and now we're saying sample size, the probability of getting 2 girls, and multiply those, and then you will get your expected number of families. 38.2 families are expected to have 2 girls. Okay, tough problem because of several reasons. I mean, first of all, finding this probability in the beginning, and then taking that probability a step further even to find a probability of 2 girls in a family, and then finally applying an expected value formula. So kind of tricky considering we just got into this topic. So I hope you followed along what's going on here. But don't worry, practice will help you feel more confident. And this was one of the latter problems in the problem set, so it is considered a tougher problem for sure. Okay, here's one more. Let's try this one. Read the question, see if you can figure this out here. Okay, so A, here's our distribution, binomially distributed, 20 trials, and a 0.2 chance or 1 in 5 chance to guess a problem correctly. And now, so that's the distribution. You could have drawn a table as well. The mean and variance are given here. And then finally, what is the probability a student answers the test purely by guessing, and they will achieve a score of 10 or more. So we're looking for probability x is greater than or equal to 10. So we can do the complement of that, 1 minus the probability of x is less than 10, because this can be run as a binomial CDF on your calculator. So try that now, 1 minus, and then run this as a binomial CDF. Alright, it's that. When you entered this as a CDF, you should have put 9 because it's going to include 9 in your cumulative probability. So